Hi everyone and welcome. EET1021. This lecture is on chapter 22, and the concept that we're going to cover in this chapter is called the RC and LR time constants. So before we get into the actual topic of time constants, let's take a quick review of resistance. As we know from previous lectures, resistance has only opposition to current. There is no reactions to changes. And resistor has no concentrated magnetic field to oppose a change in current like the inductance, and no electric field to store charge that opposes a change in voltage like capacitance. In other words, what we have learned so far about resistors is that they only oppose current on the circuit. Okay, they don't have any reactance. That's why the opposition to current on the resistor is called resistance only. When we talk about inductors, as we may recall from previous lectures, that inductors have something that is called reactance. Instead of resistance, we call it reactance. It's opposition to current, but that reactance is due to a reaction that the inductors have when the current changes. Okay, the reactance is not a actual effect of the current itself, but the change of current. How fast the current changes through a inductor. That's how the inductors produce the induced voltage and produce also a magnetic field that opposes the change in current. And the electric field also, the stored charges in the capacitor, that is another type of reactance. That's capacitive reactance, and this reactance is the opposition to the change in voltages, not the change in current, but the change in voltages in capacitors. Okay, so the three types of oppositions that we have is called resistance, which is from the resistors, inductive reactance from inductors, and capacitive reactance from the capacitors. So let's see, if we have a circuit that has a source of voltage and a resistor, only resistance, no inductors or capacitors in it, but using Ohm's law, we recall that Ohm's law can be calculated by the current on a resistive circuit can be calculated by dividing the voltage over the resistance. In this case, we have a circuit that has a resistor and of 10 ohms, a voltage source of 10 volts, and the circuit is open. However, as soon as we actually close this circuit, okay, when we close the circuit right here, let me delete this, okay. So this is the circuit, and as soon as we close the switch, this switch right here, then we have a closed circuit. And what happened with the current that is calculated by dividing the voltage by the resistance, that will be 10 divided by 10 equals 1 amp. Okay, this voltage goes from zero. The current goes from zero when the switch is open. There is no current. So as soon as we close the switch, the current goes from 0 to 1 amp instantaneously. Okay, and then will remain at that level of 1 amp as long as our source and our resistors remain the same. So this is the concept of current on a purely resistive circuit. The voltage divided by the resistance, and whatever that value is going to be the current that instantaneously happens on the circuit. Okay. With that being said, Now let's talk about what happens when we have a circuit that has resistors and inductors in it. So the action of an RL circuit during the time current builds up to a specific value, it is the transient response. So transient response is a temporary condition that exists only until the steady state current is reached. The transient response is measured in terms of the ratio L/R, which is the time constant. And we're going to use the capital letter T to identify the time constant. So the time constant on the LR circuit will be calculated by dividing the inductance over the resistance. The time constant is a measure of how long it takes the current to change by 63%. So now let me go ahead and explain this. If we have a circuit, okay, that has resistance and inductance, unlike the purely resisted circuit, that when it is closed, the current that goes from 0 to the steady state, which is in this case will be 1 amp, is instantaneously. Okay, that current will go from 0 to 1 amp at the very moment when you close the switch. When we have a circuit that has an inductor in it, as we may recall from the inductors chapters or previous lectures, we said that this inductor will act as a short circuit if there is no change in current. In other words, if we have a DC voltage applied to this circuit, so far we know that because this is a DC, so this inductor will have no reactance, will not react because there is no change in current. The current will be the same of 1 amp because 10 divided by 10 equals 1, so that will be 1 amp will be the steady state current of this circuit. However, when the current goes from 0 to 1 originally, okay, that is a change in current. The current goes when the switch is open is 0 because there is a break here, so there is no current flowing through the circuit. As soon as we close the circuit, the current will change from 0 to 10. So there is a change in current. Obviously, after from 0 to 1 amp. So there is a change in current, and once it gets to 1 amp, then it will be what we call the steady state value, which will remain there. There will be no change, so the inductor will actually behave as a short circuit. The current just will go through the coil like a regular wire, and we have no reactance at all because we're not applying a change in current. Okay. However, at the beginning, when we close the switch, for the current to go from 0 to 1, remember the if it's only resistance, then it will go like this. It goes automatically on the very instant when you close the switch. The current will be automatically 1, and then will continue and stay at that value forever if we never remove the source. Okay, but we do have a inductor now. Okay. So even though this is a DC source, keep in mind that the current is going to be 0 amps when the switch is open, and as soon as we close it, then it will go from 0 to 1. There is a change. So this will have a reactance. It will have a reaction to that change in current until it actually gets to 1 ampere, and then it will remain like that, and this one will behave as a short circuit. Okay, that time that takes from 0 to 1, this time is called the transient response. Okay, transient response. And in the case of the inductors, the transient response lasts until the current reaches the steady value of 1 amp in this case. Okay, so how we calculate this transient response is by finding the time constant. Okay, the time constant for a LR circuit will be calculated by dividing the inductance by the resistance. In this specific case, the inductance is 1 Henry, the resistance is 10 ohms, so the time constant T will be 1 divided by 10, which will be 0.1 second. Okay, the time constant T is expressed in seconds, okay, because it's a time. So as soon as we close this, okay, the current is going to go from 0 to 1. During that change, this thing is going to charge until it becomes a short circuit. Okay, and we're going to use the time constant of this circuit, okay, to identify the time is going to take for the inductor, for the current to reach the steady state of 1 amp on this circuit. Okay, so the time constant is calculated again by dividing the inductance divided by the resistance on the circuit, and that will be 1 divided by 10, and that will be 0.1 second. That's how long it takes for one time constant. Okay, now what is the one time constant represents? It represents the time that it will take for the current to rise 63.2% of the steady value. So in one time constant, in this case would be 0.1 second, the current will go from 0 to 0.63, and it will continue after that until it reaches the steady state of 1, or the value of 1 amp, which will be the value that will remain after that. Okay, so this point right here, the steady state value is reached after 5 time constants. Okay, so we're going to calculate the time constant of the circuit by dividing the resistance, the inductance divided by the resistance, and that will give you the time constant. And it will take 5 of these time constants for the circuit to reach, to the current to rise all the way up to the steady value that will remain after that. Okay, to behave just like the purely resisted circuit. All right. So when it comes to LR circuits, or circuits that have inductors and resistance, the time constant is calculated by dividing the inductance by the resistance. Okay, and it will take 5 time constant for the current to reach the steady value of which will keep from that point on. Okay, and it will be steady because the source is a DC source. Remember, these inductors, they have no reactions to DC currents. Okay, this is DC. The only time this is going to react is when the current, when you turn the switch on or you turn on the circuit, and the current will change. Instead of going automatically to 1, it will take a little bit of time to get there because of the reaction of this inductor to the change in current, from 0 to 1. Once it gets to 1, because this is DC, it will remain at the same value. Okay, so this whole 5 time constants is called the transient response, and the time that it gets for the current to reach the first 63% of its value, it will be a one time constant. Okay, 5 of these will get you to the steady state value. Okay, so when an inductive circuit is open, the time constant for the current decay becomes very short because the time constant L over R becomes smaller with the high resistance of the open. Then the current drops towards zero much faster than the rise of current when the switch is closed. The result is a high value of self-induced voltage across the coil whenever an RL circuit is open. So this high voltage can be much greater than the applied voltage. Basically, this is what this means. Okay, so if we go back to the concept that when we close this switch, this inductor will react. Remember, it reacts to the change in current. So the current is going to change from zero to 1. Okay, during that, the time that it takes to get from 0 to 1, that's called the transient response. The time it takes about to rise 63% of it, that will be one time constant. 5 of this will take you up to the to here. Okay, so it takes 5 time constants. Now, the time constant is obtained by dividing the inductance over the resistance. Okay, in this case we have a resistance, a set amount of resistance of 10 ohms, and that's why it only takes 1 second. Now, notice that the resistance is in the denominator, right? So the bigger the resistance, the smaller this value is going to be. So when it comes to when we close the circuit, right, it will take this long for this to get all the way to 1, and then it will remain there. Okay, and the time constant is 0.1 second because the resistance is only 10. So when we divide 1 Henry divided by 10 ohms, you know, you get a large amount, or 0.1 second. So what happens if the resistance is large or very large? Okay, so if you have a very large resistance, what you have here is, let's say instead of 10 ohms, this was 1000 ohms. Then you will get 1 millisecond. If this is 1 mega ohm, 10 mega ohms, then you get a very small time for the time constant. Okay, so if we take a look at this circuit right here, okay, if we have this switch closed the way it is in there, so if we have this 8 volts, this resistor is not doing anything there because it's shorted through this switch right here. So the current goes through the switch and not through the resistor, and this represents the internal resistance of the coil. So if we have this, let's say this is the light bulb right here, and we put 8 volts across this one, all this thing is going to charge. The time constant is going to be 2 henries divided by 100 ohms. Okay, and that would be 0.02 seconds. That would be the time constant, and it would take 5 times the time constant to get to the actual current of 0.08 amp. Okay, now if we open the switch, and before we do that, you know, this light bulb is not going to light up because this light needs 90 volts in order to turn on. Okay, and this is the conditions of our circuit. We have this circuit with this switch closed right here. We have an inductor here, and that inductor has a resistance of 100 ohms. So if we do this, divide A divided by 100 ohms, the current will be 0.08 amp. Okay. However, there will be a time transient response for this circuit. Okay, that would be the inductance divided by this, and that would be 2 divided by 100. That would be 0.02 seconds before this inductance becomes a short, and now the current will go only through the resistor and as a 0.08 amp. Okay. Now, what happens when we open the circuit? I mean, when we open the switch. If this switch is open, now no current goes through here, so the current has to go through this resistor. This resistor has a value of 4,000 ohms. Okay, so now we have a resistance of 4,000 plus 100. That will be 4,100 ohms resistance. And the inductor has an inductance of 2 henries. So what would be the time constant for this circuit now? So the time constant T will be 2, right, divided by 4,100. How much will that be? It will be a very small amount of time, right? Very, very, very small amount of time. It would take five of these to reach the steady state. However, before that happens, because this change, it takes such a little bit of time, so in other words, the current will be changing real fast. Okay, and remember, the inductors produce induced voltage according to the rate of change in current. So if the current changes real fast, the induced voltage that generated by this inductor is going to be very high. And now this light will turn on. It will be for an instant, for like a flash, but it will come on because when we open a circuit that has an inductor, we have to expect that the voltage that this thing is going to induce on the coil, it will be a very high voltage, because it goes the open circuit basically has an infinite resistance. It's very large resistance. So, and the resistance is in the bottom of the fraction. So the larger the resistance, the smaller the time is going to be, the time constant. Okay, so the smaller the time, that means the current is changing in a very little time, so it's changing real fast, and the inductors induce voltage according to the rate of change of the current. Okay, that's why if we have only 8 volts applied here with the switch closed, so the 8 volts goes to this resistor, so the current is only going to be 0.08. However, if we open this circuit, the resistance becomes very high in here, so, and then the time constant is going to be very, very small. That means that the current will change real quick through the inductor. This inductor generates a very high voltage, induced voltage, because of the fast change in current, and that will make this light turn on. Okay, now it will discharge real quick, but for at least for an instant, this thing will flash, because the voltage across the induced by this inductor will be very large. All right. Now that we have covered the RL circuits, we will continue in our next video with RC circuits that contain capacitors. Instead of inductors, We're gonna be dealing with capacitors and resistance now. Okay, for now, let's take a break, and I'll come back with the second part of this chapter, which will cover the RC time constants